Welcome back. Today we're going to talk about another type of ODE, which is called an autonomous ODE. I wonder how long it will take for that smash meme to get old. It doesn't matter. I'm committed to it. We're doing that for the rest of the quarter. So today we're going to define an autonomous ODE, and then we're going to solve autonomous ODEs using integration. Then we're going to look at a visual representation of an autonomous ODE, which is called a phase chart. An autonomous ODE is a special variety of separable ODE, one that can be written in the form y prime equals a function of y only. So what's interesting about autonomous ODEs is that the differential equation doesn't actually contain any instances of the independent variable x or t or whatever you're using. Examples of autonomous ODEs arise frequently when you're dealing with population growth, either short-term exponential population growth, which just has the form maybe p prime, p for population is some number times p, or for a more accurate representation of population growth, especially in the long term, we have this logistic population growth equation, which we saw in video 1. That equation is given here. The rate of change of population over time is proportional to the product of your existing population and the amount of space that you have left relative to the environment's carrying capacity, which is the maximum population that the environment can sustain. In this differential equation, since r and k are constants, we have p prime on the left and a function of p alone on the right side. So you're not actually seeing the independent variable, t in this case, play a role in this differential equation. This would be an example of an autonomous ODE. Now, because autonomous ODEs are just special instances of separable ODEs, we already know how to find the solutions. So let's, for example, solve the ODE, which corresponds to the following real-world logistic population growth problem. The population has a carrying capacity of 10,000 members. The carrying capacity is denoted by K, traditionally speaking, so I'm going to make a note that K is 10,000 in this problem. Now, when no time has passed, we're told that the population at that time is 100 members. Now, in the logistic differential equation for population growth, there's this constant multiple here called r, which represents how fast the population is growing. R might be large for something like rabbits, which reproduce quickly, and might be much smaller for something like elephants, which reproduce slowly. In this particular problem, we're given a growth rate of r equals 0.2. So let's use those pieces of information and find a formula p of t, which gives the population at time t. So what I'm going to do is I'm going to use these parameters to fill in the general population growth ODE that was given on the previous page, which said that p prime was equal to the growth rate r times p times 1 minus p divided by 10,000. I'm just going to quickly simplify this just a little bit and rewrite this as 0.00002 times p times 10,000 minus p. Just factoring that 10,000 outside of the parentheses and incorporating it with the 0.2. Now, we have an autonomous differential equation, which means that it's separable, which means that I can solve this by pulling the entire expression containing p's to one side to join p prime and integrating. integrate the left side with respect to p, and integrate the right side with respect to the independent variable, in this case t for time. Now, it's common when integrating an autonomous differential equation to need to do partial fraction decomposition. In this case, I'll need to decompose the fraction in the left integral in order to be able to integrate it. So I'll use my usual trick of Heaviside cover-up method. This looks like 1 over 10,000. And this one looks like another 1 over 10,000. So integrating term by term, we get 1 over 10,000 times natural log absolute value of p minus 1 over 10,000 natural log absolute value of 10,000 minus p, negative because of chain rule, because of the minus sign on the p. That is equal to 0.00002 times t plus c. So let's do a little bit of cleaning. I'm going to go ahead and multiply through by 10,000, natural log of p, minus natural log of 10,000, take away p, is equal to 0.2t plus a newly refreshed arbitrary constant. Let's combine those logs. And let's banish this natural log. And I'm just going to cut to the chase a little bit. You've seen this procedure several times where we apply e to both sides and then bring a constant k into the front. So now let's go ahead and let's try and use this equation to isolate p. Let me begin by clearing the fraction. So this is going to be 10,000 times k e to the 0.2t minus k e to the 0.2t times p. Gather all the terms that contain p to one side. And then factor and divide. Now, some of you may be wondering why I have not yet decided to take the 10,000 times k in the numerator and combine these two constants maybe into a new refreshed k. The issue is that in this expression, the 10,000k in the numerator is not the only place that the symbol k appears. So because there are two k's in this expression, one which is multiplied by 10,000, but the other which is not multiplied by 10,000, I can't wrap 10,000k into a new arbitrary coefficient because it's going to create a discrepancy between the k in the numerator and the k in the denominator, and that's not allowed. If the same letter is used in two places within the same expression, it does have to represent exactly the same value. And that would be broken if I decided to combine 10,000 and k in the numerator. So I'm going to leave it like this. The last thing that I'm going to do is I'm going to use the data given about the initial population to find the value of k. So 100 gets plugged in for p, 0 gets plugged in for t, and I get 10,000 times k over 1 plus k. If I solve this for k, I get 100 plus 100k equals 10,000k, which implies that 100 divided by 9,900, or 1 over 99, is the value of k. We can now say that the population at any given time t is represented by the following formula. 10,000 times k e to the 0.2t divided by 1 plus k e to the 0.2t. Now, as the previous example has revealed, solving an autonomous ODE is usually possible, but it's not always fast. In particular, the calculation that I did for the previous exercise filled up 3 pages worth of work, and although I do tend to write kind of large, that's still a lot of work. So there's a special trick that you can use when you're working with autonomous ODEs to figure out what will happen to the value of y in the long run, even without finding a formula for y. In other words, you can figure out the limit as x approaches infinity of y without solving for y. This can be an advantage if you're doing a sustainability problem, for example, and you want to know whether a population is going to grow, stabilize, and be healthy, or if the population is eventually going to die out. So in order to make that possible, we're going to construct a graphical representation of an autonomous ODE, which is called a phase chart. I'm going to construct a phase chart for the autonomous ODE given below, y prime equals 3y, y minus 1 squared, y plus 5. Now, it would be possible to solve this autonomous ODE and find an actual formula for y, but the truth is that I'm kind of dreading doing that, because not only is it going to involve what will probably be a pretty hefty partial fraction decomposition, but the act of algebraically solving for y seems like it will probably be a big pain. So instead, we're going to construct a phase chart for y, and we're going to use the phase chart to predict what might happen to y in the long run, what it might do over a long period of time as x goes to positive infinity, without actually solving for y and going through that process. So the first thing that I'm going to do in drawing the phase chart for this autonomous ODE is I'm going to set up a vertical number line. In some sense, I'm going to set up a little y-axis. And on this y-axis, I'm going to mark what are called stationary points. Stationary points are points where the value of y prime is equal to 0. They're called stationary because if y prime does equal 0, if the rate of change of y is 0, then that means that the value of y is going to be constant. So the stationary points are locations where, if y achieves this value, it will never change after that point. Y prime will be equal to 0, and y will be stuck at that value forevermore. Stationary points. So in the ODE, I'm going to take the y prime and replace it with 0 to determine where these stationary points are located. And it looks like if y is equal to 0, or if y is equal to 1, or if y is equal to -5, then y prime will be equal to 0. And so these 3 values are stationary points. If y ever reaches these values, one of these values, then y prime will become 0, and y will be stuck at those values because y prime will be 0, which makes y constant. Now, by marking the stationary points on this number line for y, on this y-axis, we have divided the y-axis into 4 regions. Now we're going to figure out whether the sign of y prime is positive or negative at each of these regions. In order to determine the sign of y prime in these regions between stationary points, I'm going to go into each region one by one and pick a test value. For example, in the first region, the one which is above y equals 1, I might, for example, pick the test value y equals 2. Let's see what the sign of y prime would be equal to at this location. So if the y is equal to 2, and I plug that into our differential equation, I get y prime is equal to 3 times 2, 2 minus 1 squared, 2 plus 5. This is a product of positive numbers, so y prime would be greater than 0 in this region. To reflect that, I'm going to go into the phase chart, and I'm going to decorate the region above y equals 1 with arrows that are pointing upward. What this communicates to the reader is that if y is greater than 1, then y prime is going to be positive, which means that the value of y is going to increase. The value of y is going to move up along this number line. Let's repeat the process for a y value in the second region, the region between 0 and 1. Maybe I'll pick a test value of y equals 0.5. So if I plug in this test value, I get 3 times 0.5 times 0.5 minus 1 squared times 0.5 plus 5, which is again a product of positive numbers, so y prime is again positive. So I'm going to decorate our phase chart with upward pointing arrows between 0 and 1. What this communicates is that if the value of y ends up between 0 and 1, then the y value is going to increase. It's going to increase until it reaches the stationary point of y equals 1, and then it's going to stop. Region number 3. Maybe I'll pick a test value of -1. In that region, y prime is 3 times minus 1 times minus 1 minus 1 squared minus 1 plus 5. This is positive number times a negative number times a positive times a positive. So in this region, y prime is less than 0. So what do you think I'm going to do to the phase chart to reflect the fact that this time y prime is negative, so the value of y is decreasing? In this case, we'll just use some downward pointing arrows. If the value of y ever ends up between 0 and -1, then the y value is going to decrease until it reaches the stationary point at -5. And finally, for -6, in the final region, the y prime value is going to be 3 minus 6 minus 1 squared minus 6 plus 5, which is positive times negative times positive times negative, result positive, and therefore I would decorate that region with upward facing arrows. So here is the final draft of our phase chart for that ODE. If the value of y ever ends up at 1, 0, or -5, then the value of y will remain at those points forevermore. If the value of y ever ends up above 1, then the value of y will continue to rise without limit. If the value of y ends up between 0 and 1, then the value will rise until it hits the stationary point at 1. But if the y value is between 0 and -5, it will decrease until it hits the stationary point at -5. Finally, if the y value ever ends up below -5, then the y value will increase until it hits the stationary point at -5. Now notice something about the stationary points in this phase chart. In particular, -5 and 0. If y is near -5, either above or below, and over time, the y value will eventually become -5. So put your y value anywhere slightly above or below -5, and it's going to get sucked in toward this stationary point. Almost the opposite thing is happening at 0. If you start anywhere near 0, then the y value is going to move further away from 0. These arrows are pointing in the direction away from 0. So we have some terminology. We have stationary points, which are locations where y prime is equal to 0. And stationary points come in two special subvarieties. A stationary point is called stable, or it is called an attractor if y values that start close to the stationary point eventually become the value at the stationary point. A stationary point is called a repeller if the opposite happens. If y values that start close to the stationary point move away from the stationary point. For example, in the autonomous ODE that we used for our phase chart demonstration, y equals -5 was an attractor, and y equals 0 was a repeller. Let's try it one more time and go back to the autonomous ODE, which corresponds to long-term population growth. dPdt is equal to the growth rate times the population times 1 minus the population out of the carrying capacity. So the first thing that I'm going to do is set up a number line which represents the values of p, and I'm going to find out what the stationary points are. So I'm going to figure out the populations at which the rate of change will fall to 0. This occurs at 2 points. When the population is 0, there is no one around to give birth, so the population will remain at 0 forever. And when the population is at carrying capacity, when p is equal to k, the population can no longer grow, because that is the limit of what the environment can sustain. Now, let's figure out the regions on which dPdt is a positive or negative number. For example, what if we considered a value of p, which was equal to 2 times the carrying capacity? If the population suddenly spiked to well above carrying capacity, for example by a sudden inward migration, what would the population do over time? Now let's reason this through. Realistically, if you got a sudden influx of members, more than what the population could sustain, the population would decrease over time due to unfortunate situations like possibly starvation because of lack of resources, or war, or competition of that kind. Let's see if this is reflected mathematically. If I plug in 2 times k to our ODE, and simplify this, r is a positive number, 2 times k is a positive number, but 1 minus 2 is going to be a negative number. And sure enough, we can see that if we're greatly above carrying capacity, that the population is forced to decrease until it reaches more sustainable levels. What if we picked a population that was greater than 0, but which was below carrying capacity, maybe k over 2? Intuitively, we might guess that the population would increase in that case. The population is greater than 0, so there are still members available to reproduce, but the environment can still sustain more people, more members, and so there aren't any limitations on the population yet. Mathematically, if I plug in k over 2, then I get r, k over 2, 1 minus k over 2 divided by k, which simplifies to plus, 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 a product of 3 positive numbers, and so that results in a positive number, as we expected. Now, in practice, it doesn't really make sense to have a negative population. So I'm going to actually ignore this third region, just because a negative population doesn't make sense. If the population reaches carrying capacity, it will not naturally change much from that value. There would have to be some sort of disaster or migration event. If the population ever rises above k or below k due to one of these unusual circumstances, then over time the population will be drawn back toward the carrying capacity. And so in the language of the previous page, we would say that the carrying capacity is an attractor. Over time, the population will be drawn toward this value. That concludes today's material. We talked about an autonomous ODE, how to recognize an autonomous ODE, and how they can be solved, including in initial value problems. We talked about a graphical representation of an autonomous ODE, which is called a phase chart, and how to analyze phase charts to determine what will happen to the value of your dependent variable, y or maybe p, over a long period of time. What's going to happen to the value eventually?